Hello everyone, we are group 20 from Information Hub. Yeah, our group members are Yecheng Lu from AI Thrust, Li Yao from DSA Thrust, and Huan Xunpeng from AI Thrust. The topic of our presentation is recovered meaningful representations for bidirectional generative models. Here we list the outline of our presentation. We will first introduce some backgrounds and problem settings by Huan Xunpeng. Then we will introduce our work, including the proposed algorithms and its theoretical analysis by Yecheng Lu. Finally, Li Yao will present our experimental results on artificial and real-world data sets. With the popularity of generative models to investigate the semantic meaning of vectors in latent space become very popular. Such investigations are very useful in several fancy applications, such as the style transfer. A very interesting observation is that the semantic change of given images can usually be considered as some certain transformations in latent space of generative models. For example, given one image about the anime face, if we do some interpolations in the latent space, we will easily notice that the image obtained by decoding the transferred latent vector showed another meaningful pose. And in the meanwhile, its dual task, recovering the meaningful latent structures, also attract much attention. Roughly, it requires each dimension of latent space contains some certain semantic meanings. However, this task is known to be difficult in fully unsupervised setting, and recent studies consider the use of auxiliary variables such as class labels to help the recovery of true latent representation. Here, we compare the previous work and our work to show our contributions. The main limitation of previous work lie in the constraints of the model capacity, including the limited distribution family of conditional prior and the requirements of deterministic or additive Gaussian generators. To allow more complicated prior and generators, we expand the identifiability theory of the generative model, present a practical algorithm, and validate it on the artificial and real-world dataset. Then I will introduce some notations and basic models to explain what is the meaningful representation. We use the X to denote the observed variables such as images in digital datasets. Besides, we may have some other auxiliary variables which can contain much information such as the color, the shape of objects, or digital labels in the data. We assume the joint distribution of the observed auxiliary variables pair depends on the prior of auxiliary variables U and the conditional probability X given U. Suppose our default latent space is Z, whose dimensional number is L, while only an n-dimensional subspace of Z is meaningful. To coupling the auxiliary variables and meaningful latent vectors, we require a conditional factorized assumption, which denotes the vector belong to meaningful latent space will depend on our auxiliary variables, and the vector beyond the meaningful latent subspace provides some probabilities like some noise.
Present the algorithm and the theory part. First of all, let's consider a conditional bidirectional adversarial generative model. We call it bidirectional because it has the encoding and decoding part, the two directions. The decoding direction is like this. We first put the latent features Z to the decoder G and to produce the data GZ. And the encoding direction is like this. The data X is transformed by the encoder E to the latent features EX. And the additionally observed variable, also known as the label U, acts as an input of the prior FC net, the encoder net, and the discriminator. Our goal is to match the two joint distributions of GZC and XEXU. In the algorithm identifiable age, we input the training set, the initial parameter, and the batch size. Then, for multiple steps, we sample the observed and additional observed data X and U from the training set, and sample the latent variable data points Z from the prior P beta Z given U. Then we update the parameter for the discriminator by descending the stochastic gradient in this equality. After that, we also sample the data as above, and we compute the gradients for the parameters in the decoder, encoder, and prior. Until convergence, we repeated the steps above. Intuitively, the identifiability means that the estimated latent variables and the true one have a component-by-component correspondence. And the definition for this identifiability is shown as follows. For example, for this data below, the true latent variable has two dimensions, the size and color. If the recovered latent variables has one dimension corresponding to size and another to color, like the first row, we say that the latent distribution is identifiable. Otherwise, the color, size, and color factors are entangled, like the second row. To achieve the identifiability, we not only need additionally observed variable U, but also need it to have significantly and variably influence on the conditional density of the latent variable Z, which are called the variability conditions. The conditions can first, the entangled function space projected on the domain of U becomes the null space. And since the functions from the latent variable to the estimated one are injective, the map must be one by one. And then we use a Gaussian example to validate these conditions. This is the two-dimensional Gaussian variables, and we let the auxiliary observed variable U be the segment discrete labels 1 to 5, which means that there were 5 clusters for the latent variables, and the Gaussian latence Z has a distribution where its mean and variance parameter from each cluster are randomly sampled from 2 intervals. Because the parameters are sampled independently, the situation that the vectors mu1 sigma 1 square and mu2 sigma 2 square for 2 different values of U are collinear is generally impossible. Finally, the main theory is presented as follows. As long as the injectivity and smoothness of the distributions and the variability conditions are satisfied, our algorithm can guarantee that the latent variable's density is identifiable.
In this section, we use artificial data and a real-world data to show the effectiveness of our method. In the artificial data, we sample the ground truth latent variables from a two-dimensional multivariate Gaussian and equally divide them into 5 clusters, as shown in Figure 1a. The cluster labels are used as additional variables U. We combine the two-dimensional ground truth samples with 8-dimensional small Gaussian noises to form a 10-dimensional latent space. Then, the observations are generated from those latent samples by a randomly initialized 3-layer MLP network. We choose all the networks to be MLP and utilize IH with implicit generator, Gaussian encoder, and prior to estimate the parameters. We also train the model with other methods under the same architecture. We evaluate the quality of learned representations in 2 aspects. First, to validate their variations concerning U, we compute the mean standard derivations inside each cluster for each dimension and sort them by size, called spectrum. Second, to evaluate the performance of identifiability, we adopt the mean correlation coefficient. First, we realize the original latent factors, observations, and recovered latents in Figure 1. The representations learned by IH almost recover the latent structure with no dimension rotations. Second, Figure 2 shows the spectrum, PCC, and MCC. From Figure 2a, the 2 informative dimensions recovered by IH can be clearly distinguished from those noises. From Figure 2b and 2c, the recovery of IH has a higher correlation with the true informative factors. We apply our method on real digital dataset EMNIST. The digital labels are utilized as auxiliary observed variable. We set the dimension of the encoded latents to be 50. We compute the variations for different auxiliary information that we have grasped, such as a digit number for EMNIST. We measure the variations by the standard derivation of a single dimension when U takes different values. We show how the image changes when traversing a single informative dimension in Figure 4. Compared to gain, the sharp knee of latent variables encoded by IH appears earlier. In conclusion, we extend the identifiability theory of bidirectional generative models to a more general setting and present the IH algorithm. For noisy image dataset EMNIST, the implicit encoder and generator give the IH model an edge over others using Gaussians. The representations learned by IH are more interpretable, concentrate the key information, and not corrupted by noises. Our theory guarantees the distinguishment of the latent representations that has potential benefits in downstream tasks. In the future, we would like to explore the potential of our proposed theory and algorithm on larger scale data, as well as the combination with the emerging unsupervised representation learning area. That's all. Thanks for listening.